but you can't use it on the internet. These addresses are legal addresses. You could have them, but they're not allowed to be used on the internet. Bottom dot. Can't be routed across the internet. Good. My phone stopped ringing. APIPA, the bottom one. That means you're trying to get an address from DHCP, but it failed. Now, I can't warn you enough. Be sure to understand from last week how DHCP is different than DNS and how DHCP and DNS are different than ARP. Nevertheless, APIPA is a secret number of addresses that you get if DHCP fails. Those 169.254 addresses are also illegal to be used. And you say, wait a minute, what do you mean they're illegal to be used? If you can be assigned that address, how can it be illegal? Yes, if you can get that address, there's only one way you should be able to get it. DHCP failed and APIPA gave it to you. You should never be given that address any other way. See what I mean? Is it a legal address once you get it? Yes, but you shouldn't be assigned it any other way. When would that happen? Only if DHCP fails. Now, this is important, and this will be on my test, so we're going to go over the second time, the CIDR stuff. I'll go right to here. I would have to have a 172.31.210, and that's the mask. I need both of those numbers. When I'm too lazy to write two numbers, I have to write this number and this number. Why don't I just write this number with a /24? Now, where does 24 come from? Well, where this 24 came from was, oh, screw you. Okay, I don't know how all that came up here. Let me get rid of this. And I don't know how to get rid of this. Okay, let me just do this. So if screw you. Okay, so this 255 is what? This 255 is 8 ones and zeros. This 255 is what? It's 8 ones and zeros. This 255 is what? It's 8 ones and zeros. That's where the 24 came from. So let's say I do something like this. 10.x.x.x. And the subnet mask is 255.000. An easier way to write this is /8. Where did I get the 8 from? Because there's 8 ones over here. What if I did this? What if I did 132.14.x.x? And the subnet mask is 255.255.0.0. Wouldn't it be easier to just write /16 over there? Where did I get the /16? There's 8 bits here and there's 8 bits here. That's /16. Now, I want to point out for the second time, nobody's going to ask you to go. Everybody says, yeah, I understand how you went from here to here. They're not going to ask that. They're going to say, if you have a /16, what's the equivalent subnet mask? If you have a /8, what's the equivalent subnet mask? And if you have a /24, what's the equivalent subnet mask? Yes, you do have to know all this stuff. I'm assuming the dead silence means you are understanding this, and if I put it on my test, you would know it, because we will not be going over this again. If anybody wants to ask me anything, they can, but that's called the CIDR notation, and this is used a lot in real life. As a matter of fact, I'm going to get to it on a slide coming up. You should be able to read this if you read a magazine article. Screw that. And we talked about the subnet mask. That's the 255. Now, I'll give you my little speech again one more time. It's variable length custom subnetting. It's a 2 or 3 hour lecture. Well, the good news is you're not going to get it now. The bad news is you are going to get it in December sometime. So we're going to have a whole evening, or maybe two meetings, where we do variable length subnet masking. The reason for that is it's very important to know, but it's also very difficult. So it will not be on my final exam, will not be on the next exam. But for the smart people, I do want to cover it, and I will cover it. That way you won't be shortchanged by the class being online. It's difficult, but it's not the end of the world. And if I cover it right over 2 nights, you should be able to get it, especially the smart people. So we're going to skip that for now. And I'll refer back to this chapter when I'm doing that. But I've got, well, that's another problem. I've got some handouts for that. Well, I can't really give handouts, so I'm going to email some of those things to you before the thing, and you can print them out, and then we'll see the best we can do. It's a compromise when you do it online, but we are where we are. So we're skipping all this. Now, again, we're not really skipping it. We're postponing it till December when you are going to get it. Okay, let's go down this. This is very important. Then I have to go to the new material. Class A, Class B, or Class C. It's got to be one of those three. So for my test, there's only three possible subnet masks. 1 255 and 3 zeros, 2 255s and 2 zeros, or 3 255s and 1 0. Those are the only possibilities. Class A is 1 255. Class B is 2 of them. Class C is all three of them. Okay? Know what Class A, Class B, and Class C. Second dot, every time you have an address, you must have a corresponding mask. Now you can display the mask as 255, or you can display the mask as /24 or /8, but you must have the mask there. All hosts must share the same network ID. Well, what does that mean? If I'm 192.168.12.9, then you can be 192.168.12.10, and you can be 192.168.12.11. But nobody can be 192.168.13. We all got to be 192.168.12. That's what they mean, the same network ID. But the hosts have to be unique. If I'm .13, then you got to be .14. And if you're .14, he better be .15. And if he's .15, she better be .16. See what I'm saying? That's what they're getting at for all these two things here. And I'll do this one, which I didn't do last time, but I want to make the point about different network IDs communicate. We said a 1412 guy can't communicate with a 1413 person. What's the solution? We'll change the 1413 person so he's back on the 1412 network. Yeah, but I don't want to do that. Can a 1413 person ever communicate with a 1412 person? And the answer is yes. You know when they can do it? If they go through a router. Why? Everybody in one subnet can communicate with everybody in the same subnet through a switch. But everybody in one subnet cannot talk to anybody in a different subnet unless they go through a router. Because our subnet is a separate LAN, and routers connect LANs. So the 1413 person can talk to the 1412 person as long as he or she goes through a router. Peter Piper picked a peck of pickled peppers. This was the unimportant one. Can you assign multiple IP addresses to one network card? You can, but no one ever does it. That's the unimportant one. This next one's very important. What's a multi-ohm server? Well, a multi-ohm server says a computer that has 1, 2, 3, or 4 separate network cards. Network card 1, network card 2, network card 3, network card 4. Big cuidado. You got a lot of NIC cards. What do you need? You need a separate IP address for every NIC card. Each NIC card needs its own IP address. Each NIC requires its own IP address for the network which is connected. All right? Now, I'll talk about this routing issues in a minute, but let's skip ahead to this one. So here's a multi-ohm server. This NIC card's on the 192 network. This NIC card's on the 172 network. Notice there's a /24. That means this is 192.168.1, and somebody's .33, .34, but we all got to be 168.1. This guy's got to be 16.208. something, okay? So I'm talking to the 172 network, I go out this NIC card. Talking to 192, I go out this NIC card. Now, here's the cuidado. Can somebody here talk to somebody here by going through this computer? You know what? They really can. Wait, I thought the only way one subnet can talk to another subnet is through a router. Well, guess what, Mo, Larry, and Curly? You just turned this computer into a router. That computer has been made a de facto router. And that's why what this slide says over here, multi-ohm servers can run into routing issues due to multiple default gateways being configured. Look, this wasn't meant to be a router. Whenever I have two NIC cards, it automatically turns into a router. Now, when I talk about routing issues, what I mean is this is an accidental router. Had we decided to make this a router on purpose and program this in, there'd be no problem. But if we've got regular routers doing something, and this router is there accidentally, this can cause routing issues. Whenever you have 2 or 3 NIC cards in a computer, whether you want it to be or not, it is automatically a router. And what the routers do, they connect different LANs or different subnets. Peter Piper picked a peck of pickled peppers. All right, we all got that? I'm going to keep going slowly now, and I'm going to slow down, but we should be out of here by 4:10 or 4:15. The bad news or the good news, I hope you're enjoying this lecture because you ain't never seeing this chapter again. Okay, we're going to move on to chapter 7 next week. All right, we have to do all these commands, and we are going to cover them. And then we're going to cover IP6, and then we'll be done, but it's going to take a few minutes. Again, I don't think this is a very hard chapter, but if you do, chapter 5 was TCP/IP and the concepts. Chapter 6 is TCP/IP and the numbers, and you got to know them both. All right, let's keep going. We're going to do all of these commands. ipconfig. What does it say? Display your IP address. So you type in ipconfig. What is my IP address? What is my subnet mask? What is my default gateway? A simple ipconfig says, tell me about myself. What's my subnet mask? What's my IP address? What's my default gateway? ipconfig/all adds what? Give me all those things, and in addition, show me my MAC address. In addition, show me my MAC address. And again, I could stop the lecture here, but I always do the release and renew. And why? ipconfig release and renew have to do with DHCP. Remember DHCP, 50% of the time you renew your address, 87.5% of the time you look for a new one. Well, what if I want to renew my address right now? ipconfig renew says contact the DHCP server, and even though half the time isn't up, just tell the DHCP server, I like this address and I want to keep it for a while longer. Can you do that mechanically? You bet your rear end you can. Okay? My favorite one, however, is the ipconfig release. So here's what happens. You know what? I just don't like my IP address. Well, what do you mean you don't like it? I just like it. I don't want this IP address. How can I get rid of it? ipconfig release, and you just got rid of your IP address. Now, what you don't realize is you've set a chain of events in motion. Now, why? Because now your computer's naked. It doesn't have an IP address. And what is your computer going to do? It's going to initiate a DHCP discover. Remember from last lecture, which some of you missed, the DORA process. Discover, offer, request, acknowledge. Now, ipconfig release doesn't trigger that. It just releases the address. But once the card doesn't have an address, it feels naked and it says, I need an address, who can help me? And it does a DHCP discover process and it gets a new address. Could you release a new address and force it to get a third or fourth address? You bet you could. You could do exactly that. So I thought I'd do those two simply because you should understand them from your DHCP stuff. Okay? What does ipconfig do? It's a command that shows you what's my IP address. Okay, what does ping do? It tests connectivity. Are you there? Are you there? Ping uses the second dot, the ICMP echo request and the ICMP echo reply. Gee, what's ICMP? I forgot. In chapter 5, ICMP is one of the sub-protocols of TCP/IP. So when you use the ping command, it automatically sends 4 ICMP echo requests, and it expects to get back 4 ICMP echo replies. If it does, there's connectivity. If it does not, there is no connectivity. Now, let's not confuse the ARP command with the ARP process. In chapter 5, what does ARP do? It converts or translates a TCP/IP address to a MAC address. Remember, it never goes backwards. It can't translate a MAC address to an IP address, just an IP address to a MAC address. Well, what does it do? It doesn't want to ask every time. It says, like, you just did it. So what does it do? Once it translates an IP to a MAC address, it temporarily stores the combination IP to MAC address in something called the ARP cache. So when the second and third packets come through, they don't have to re-ask again. It's a convenience. So What does the ARP command do? The ARP command simply says, show me what's in my ARP cache. ARP command displays current ARP entries in the ARP cache. Doesn't say the word ARP cache, does it? But yeah, here it is, the ARP cache. So if I want to show what's in my ARP cache, that's what the ARP command does. One more time, don't confuse ARP with DNS, and don't confuse DNS with DHCP. Ping just says, are you there? Yes or no? Are you there? Yes or no? What does traceroute do? Traceroute says, are you there? Could you show me the path you took to get there? Now, again, if you're right across the hall, ping and traceroute are going to work the same because you're not going through anything. I'm pinging you. You say, yes, I'm here. I traceroute you, and you're there. You say, yes, I'm there. But if I'm pinging you in California, all I get back is, yes, I'm here. Well, how did I get to California? I don't know. You just want to know if I'm here, I'm here. With traceroute, they'll give me a reply that you're there, but it'll also show me the exact route it took. It'll show me every router it went through to get to California. Traceroute's a command that shows me the exact path you took to get to the other computer. Ping won't do that. And finally, and I'm not done with the lecture, I'm just done with the commands. Finally, NSLOOKUP. Now, what does NSLOOKUP do? That says, I need an address. Here's an IP. Here is a name. Can you give me the address? And it'll tell you what the address is. And you say, wait, isn't that what DNS does? Well, what DNS does is if you click on a web link, it will take you to that website automatically. So with DNS, you get the address and it takes you there. With NSLOOKUP, all it does is give you the address in writing, but it doesn't take you there. So if you go NSLOOKUP, www.bergen.edu, it says, no, what, you don't want to go there. You just want to know what the TCP IP address of it is. So here it is, Joe Smith. Here's the TCP IP address of Bergen.edu. Well, why didn't you take me there? Because you didn't ask me to take me there. You did an NSLOOKUP. You just asked me its address. Well, how would I go there? Well, if you double click on it, on the actual link, it'll take you there. If you do an NSLOOKUP to the thing, it will just give you the address. But it uses the DNS process. So many people say it's the command line version of DNS. That's NSLOOKUP. Okay. NAT, this is a neat lecture, and I have time for it too. I want to translate from public to private, so watch carefully. I am this address, and I want to get what's Susan B. Anthony's birth date. But I can't go on 10.1.1 because what? Remember way back 5-10 slides ago? That's a private IP address. So I go out and ask for Susan B. Anthony's birthday as 123.01. Now watch what happens. The reply of when she was born comes back to 123.01. This guy's got to translate back that to 10.01 and answer me. Now I need different information. I need some information on the horses at Hialeah. So I ask at 10.02, but I ask the information at 123.102. When the reply comes back to 102, it's got to be translated to 02 to go to me. This guy translates public to private IP address. Now, why bother to do this? Well, why does Superman have a secret identity? So he won't be bothered. Everybody knows that 123, 101, and 102 exist, and they might be attacked. But nobody knows that 10.1 and 10.2 exist. They're completely private. Nobody could ever attack 10.1 or 2. Why? They don't know that 10.1 or 2 exists. They think that you're 123, 101, and 102. Now, do you think if they attack this guy, that the translator is going to be stupid enough to pass the attack back to you? So you get privacy on a public internet. That's network address translation. As opposed to port address translation. This is tricky. I want to go out on 10.01 and 10.02, but on the same address. Now I got a problem. I got some Susan B. Anthony information. You got some information, the horses at Hialeah, but they both come back to 100. How do I know that my information should go to me and your information should go to you? And the answer is they both come back to 100, but I am port number 5311 and you are port number 3105. Same return address, but a different port number. So let's go back to the slide. Allows several hundred workstations to access the internet with a single public address. Each one concerns the destination IP address along with the source and destination port numbers. A single public IP address for all workstations, but a different port numbers for each communication session. You're the same address as him, but you're port 2204, you're port 6895, you're port 5311. That's how I know to come back. Pat and Nat are similar, but remember what I said, people. I'm going to just pause. This is all what I call a techno-babble, techno-terminology course. So not confusing DHCP with DNS and not confusing NAT with PAT. See what I mean? That's the secret to this course. So people say, oh, they're all the same, then you're screwed. You can tell the difference, you got the course. That's what the whole course is, understanding all these acronyms and what they do. Do I like teaching it this way? I don't mean this online, but I mean this is this, this is this, this is this. What they seem to want to do with Network Plus is give you an overview of the stuff. If you take my Cisco course, we're going to do a lot of this stuff in way more detail. What they want to do in Net Plus is just hit the highlights. Is it hard? See, some people say it's easier because you're not getting so much detail, and that's true. You have to know this in detail. In Cisco, it's much harder. On the other hand, it's hard to learn that this concept means this, and this means this, and this means this, without going any deeper into it. So each one has its advantages and disadvantages. Know what NAT is and know what PAT is and know the differences. Okay, we're getting to the end of the lecture, but we're getting to the most difficult part, and that is IPv6 versus IPv4. Now, IPv4 is the standard TCP IP that we learned developed 40 years ago. What I mean is that's the 32-bit binary address. That's the one that has the Class A, Class B, and Class C. That's the one that has a subnet mask of 1 or 2 or 3 255s. Now, by the way, just because that's old-fashioned, you really do have to know that. You will not get a job unless you know that code. But it doesn't have enough addresses. So IPv4 is the 32-bit version. IPv6 is the new replacement for that. And okay, it has all these advantages. Now, I'm not going to teach all these because they're a waste of time. I'm going to only teach one advantage, and it's this one here. And watch what I'm telling you. Regular TCP IP has 32 bits. How many possible combinations of addresses is that? Well, the answer is 2 to the 32nd power. We'll do that in your head. What 2 to the 32nd power is 2 times 2 times 2 times 2 times 2, 32 times. So you multiply 2 times 2 or you double it 32 times. Well, it turns out that that's a big number, but that number is about 4 billion. That means you have about 4 billion combinations or 4 billion possible addresses. Oh, well, that's plenty. That's all I need. Well, there's a problem. Internet's going worldwide. Everybody in Africa, India, Asia all wants to have the internet now. So what we need is we need more addresses. And the big advantage to IPv6 is this one here. Larger address space or more addresses. There's more possible combinations. Next slide. We use 128 bits instead of 32 bits. So IPv4 was 2 to the 32nd power, or about 4 billion. IPv6 is 2 to the 128th power. Do that in your head. Oh, Professor, I calculated and that's so-and-so. Well, you know what? You're lying. You didn't calculate it. That number is so big, it doesn't have a number. It's not a billion. It's not a trillion. It's not a quadrillion. It's what I call a gazillion. What do I mean by gazillion? It's a number so big you can't express it. It's a huge number. So it's 2 to the 128th bit power, which gives you a number so big you can barely express it. Now, only because we have the time, I'm going to do something really sexy. This will not be on my test, but this you should know, and I think I can do it, and we do have the time. So, with the 32 bits, it was something dot something dot something dot something 4 times. 8, 8, 8, 8, and 8 times 4 is 32. Well, if I wanted to go to 128 bits, it would be something dot something dot something dot something dot something dot something. It would be a number this friggin' long. Matter of fact, it'll be longer than this long. It'll be so long I can't get my arms around it. So we have to do something sexy. So what we're going to do is we're going to write it as 8 16-bit hexadecimal numbers. There's 16 bits here, 16 bits here, 16 bits here, 16 bits here, and 16 times 8 is 128. Now, you say, Professor, I sort of got that, but I'm not sure what you're talking about. I have my little marker, and I have some really bright people in here. How do I get rid of this stupid thing up here? Yeah, good, it went away. And I'm going to go up here and touch this. Go way over here and touch this. Now, what is FE80? Well, binary F is 4 ones. Binary E is 1, 2, 3 ones and a 0. Binary 8 is 1, 0, 0, 0. And binary 0 is 4 zeros. So I've got 4 zeros, a 1 and 4. I've got 16 ones and zeros. That's the F80. Now, take my word for it. This 0 represents 16 zeros. This 0 represents 16 zeros. This 0 represents 16 zeros. Let's try 18FF. Binary 1 is 0001. Binary 8 is 1000. And binary F is 1, 2, 1, 2, 3, 4. And the next binary F is 1, 2, 3, 4. This is 1, this is 8, this is F, this is F. But that's 16 bits. Let's try 0024. Well, I'm going to leave some of it out. This is 4 zeros and 4 zeros. 2 is 0010. And 4 is 1000. I'm sorry, 0100. The bottom line is 4 bits, 4 bits, 4 zeros, 4 zeros. That's another 16 zeros. Let's try 85A. 8 is 100. E is 1110. 5 is 0101. And A is 1010. Bottom line is that 16 ones and zeros. The 60 is deceptive. The 60 is 0060. So it's 4 zeros for the first 0, 4 zeros for the second 0, 4 ones and zeros to represent the 6, and then 4 ones and zeros to represent the 0. One more time. Between each colon is 16 ones. There's 8 groups. What's 16 times 8? 128. That is how we do IPv6. Now, I'm having a lecture tonight that you're not invited to, but if you take my Cisco class, you have to actually know which letters represent which things and actually have to know exactly how to do this. Here, you just have to understand that IPv6 is expressed as 8 16-bit hexadecimal combinations. That's all you have to know. If you take Cisco, you have to know exactly what they stand for. All right? That won't be on my test, but I thought that was a neat thing to do. And I couldn't do it without the little marker, but as long as I have the marker, I could. Again, there's some pretty smart people in this class. I'm hoping the smarter people are understanding my higher level stuff, because you're the guys who are going to get the jobs, and the girls who are going to get the jobs and make real money. And I hope a lot of you do that. Oh, this is a neat one. I'm just going to talk about it. We all know what ARP is. And what does ARP do? ARP converts IP to a MAC address. Now, there's a trick to this from the last test. What's a regular TCP IP address? It's only 32 bits. What's the MAC address? Well, the MAC address is 48 bits. You're converting a 32-bit address to a 48-bit address. That's what ARP is doing, okay? And it uses the 48-bit MAC address. Well, what you can do, if you have 128 bits, 126, 128 bits, you've got enough room to do what? You can take the entire MAC address and stick it right inside. So I'm not going to worry about this exact mechanism. Well, what you can do is you can take the entire 48-bit MAC address and insert it completely into the 128-bit IPv6 address. So instead of having to use ARP to translate, you just say, hey, dig in there, and in that 128 bits, you got my 48-bit MAC address, give it to me. That's all you have to do. One more time. The 48-bit MAC address is buried inside, and then there's a rule of how it works. The first 2 digits, and then you've got to put it in the second 64 bits. You say, wait, if you're putting the second 64 bits, it's only 48 bits. Yeah, but there's certain prefixes you have, and then you have the 48-bit MAC address. So the 48-bit MAC address is put somewhere in the second 64 bits of the 128-bit IPv6 address. Peter Piper picked a peck of, Okay, we got that. I thought that was just a neat thing to put in. By the way, just a quickie, a lot of people say, well, Professor, since we're so worried about IPv6, this is taking over, could I just skip the IPv4 stuff? And I don't need to know it's yesterday's stuff, and I'll just learn this. Turns out you can't for a lot of reasons. And first of all, even though theoretically we're supposed to go to IPv6 in the future, we're still in a dual world. And you will not get a job unless you understand IPv4, unless you understand subnet masking, unless you understand the variable length subnet masking I'm going to explain to you at the end of the semester, and unless you understand how the subnet mask works. So you really have to know that stuff. If you don't know it, you won't get a job at all. I'm not saying it's good or bad. I'm saying you have to know it. Well, I'll do this quickly because I want to we're actually coming near the end. We'll be out of here in 10 or 15 minutes. Let me just put this over here. I don't think I need this in a minute. But this is kind of sexy, and I'm going to do it. I'm going to leave out the difficult stuff. Unicast, multicast, anycast. Well, we all know from the last test what a unicast is. Unicast is me to you, me to one computer. And we all know what a broadcast is. So broadcast is every computer on the LAN, and unicast is just one, just one, just one. Well, now we're introducing two new ones, a multicast and an anycast. And as long as I have the time, I'm going to put those in. We're getting near the end now. We'll be out of here in 10 minutes or so. I'm skipping all this because it's not there. Okay, a multicast performs the same one as in 4. A multicast is not everybody and not one person, but a group of you. So let's say we were in a classroom and we got a bunch of rows in front of me. I only want to send to this row in front of me here. Now, what I could do, there's 4 or 5 of you in the row, half boys, half girls. I could send to all 4 or 5 of you. I could send 5 unicasts and you'd all get it. But a simpler way to do it is send a multicast. And what a multicast is, there's an address up here in front of me. And they say, wait, professor, there's 5 people. Why are you putting a 6th address online? Well, that 6th address, nobody's sitting there. But that's for all you 5 to listen in on. So any information going to this address, you 5 can hear, but nobody else can. Now, people in the other row say over here, I'm in this row. I want to be included. Okay, I'll tell you what we'll do. You guys in this row over here, I'm going to put an address up front here. You say, wait a minute, there's only 4 of us in the row. Why are you putting a 5th address? Because any information going to this address, all 4 of you can listen in on. So the 4 of you are listening on this address in front of here, and the 5 of you are listening in on this address. That's a multicast. Multicast is to a group of you. Not everybody, not one person, but a group listening in on a fictitious address that's designed just to be a multicast address. And IPv4 and IPv6 both have that concept. Now, the anycast, I'm going to do it only because I'm here and I have enough time, and then we'll get to the end of the lecture, which is fairly difficult. And that is an anycast is a tricky one, only IPv6 has it. And it's this way. With a multicast, all 5 of you have to get it. With an anycast, just one of the 5 of you have to get it. So if there's 5 of you in a row, it's a multicast, you all have to get a copy of that information. But if it's an anycast and I just deliver it to her, it's been delivered. Now you say, wait a minute, that doesn't make sense. She got it, it's true. Well, what about the other 4? They didn't get it. Well, anycast is used to be done in a very special case. Used to be sending information. What the anycast is about is if I'm trying to contact server 1, and I've got 3 or 4 physical server 1s. Now you think server 1 is this, server 2 is this, server 3 is this. But supposing server 1 goes down, I might have 3 computers that all act as server 1. So an anycast would be, if I got to any one of these 3 addresses, I've gotten to server 1. Now, these 4, if I got to any one of these 4 addresses, I've gotten to server 2. So an anycast is if the packet or frame was delivered to any one of those addresses, it's considered to be delivered in anycast. With a multicast, multicast is tricky. With a multicast, all 5 of them have to get it, but it's not being delivered to all 5 addresses, it's only being delivered to the multicast fictitious address. So if the multicast fictitious address got it, we're going to assume that all 5 of you got it. With the anycast address, if any one of you got it, it's been delivered. And only IPv6 has that. Again, Peter Piper picked. All right? We're getting near the end, people. I'm getting tired of this, but I'm not going to do auto configuration. I'm not going to do this. Now, we're at the end of the lecture, but this is tricky, tricky stuff. So let me see if I can do it right. We're saying that TCP/IP is still in use, but we're saying that we're going to use IPv4. So you say, I'm using IPv4. I'm still using regular IPv6. I'm using IPv4. I'm using IPv6. What can we do? Well, the easiest one is what's called dual. If you buy a Windows 10 computer today, you know how it's configured? It's configured for TCP IPv4 and TCP IPv6. It's configured for both of them. Meaning, if I'm talking to the computer using IPv4, it uses IPv4. If I got another guy using IPv6, I use that. So I can be sending frames and packets to everybody, 6 sometimes, 4 sometimes, 6 sometimes, 4 sometimes. Today's computers, like Windows 10, has dual IP architecture. It's completely configured to use IPv6 and at the same time completely configured to use IPv4. You can use either one or both. End of lecture, right? We have a slight problem. Supposing I'm using IPv6 and you're using IPv6, no problem. We're going to use IPv6, right? Well, we're going to talk about this tunneling stuff. So the dual architecture means I can communicate either one. Dual stacks. There were 2 versions installed, and I can run either 6 or 4. That's the one I just said. But now we have to talk about this tunneling, and I'm going to skip this to go to this one. I'm using IPv6 and you're using IPv6. Unfortunately, we're not next to each other. We're not in the same building. You're in somewhere in Swahili land somewhere in the middle of the other side of the continent, and I'm here in Paramus. We're going to have to go over an IPv4 tunnel. Now, I always think this one. If I've got a big suitcase and a small suitcase, it's duck soup to put the smaller suitcase inside the bigger suitcase and carry them both. That's not a problem. But supposing I gave you 2 suitcases, a big one and a small one, and I said, look, I want you to take this large suitcase and cram it into this little tiny one. You say, wait, Professor, I can't do that. I can't, what am I going to fold it up? I can't do it. This is TCP IPv6. This is TCP IPv6. But you're going to go through an IPv4 tunnel. I've got to take an IPv6 128-bit packet and stick it into a 32-bit packet and then expand it on the other side to 128-bit packet again. Can I do it? Well, it ain't easy, but obviously I can. So that's what they mean by tunneling. A network protocol technique that allows transmitting a packet in a format that's otherwise incompatible with the network architecture by encapsulating that packet into a compatible packet. That means it's not 4 into 6, but it's 6 into 4. It allows a host, read this 4 times to get it, an IPv6 packet over an IPv4 network. Now, I'm not going to do the details of that because, frankly, I'm not sure I understand exactly myself how they do it. But we have to go across an IPv4 network, and we need an IPv6 packet. We have to tunnel one inside the other. It's counterintuitive. You're putting the big one into the smaller one, not the small one into the big one. Okay? It's very counterintuitive and tricky and difficult. So, there is your picture. So I'm 6, you're 6, but we're going through a 4 tunnel. By the way, it doesn't mean you do 6 to 6 directly through a 4 tunnel. What it means is you do 6 and you somehow encapsulate it in a 4 packet of 32 bits. You get it over there and then you have to extrapolate and take it out. Is it possible to do that? It does, because what they do is they take the big packet and encapsulate it with the small packet, so the tunnel thinks the small packet's going, we're really inside the small packet's the big one. I don't know how to explain that, how they do it, but that is what they do. Peter Piper really does pick a peck up. This is really tricky stuff. So, watch carefully now. ISAP is a form of 6 to 4. 6 to 4 is another form of 6 to 4. And Teredo is. Now let's go back. Dual architecture is we're doing both. I can do 6 and I can do 4. That's one thing. 6 over 4, ISAP, 6 to 4 Teredo. All 4 of these do the same thing. What do? They put an IPv6 packet inside an IPv4 packet, send it, and then take it out the other end. All 4 of these do not what this slide says. All 4 of these do what this slide says. All 4 of these do tunneling, which means they put one inside another, and all 4 of these do what I just said by putting one around the other. Now, do I have to know Teredo and 6 into 4? Not particularly. I would want to know what IPv6 is. I would want to know it's 128 bits. I would want to know that it has a larger address space. I would want to know all those things. You don't necessarily have to know the FE stuff. That I don't care about so much. Okay, now look, we covered a lot of stuff today, but I'm warning you, all that subnet masking stuff, all that /24/16/8, all that class A, class B, and class C, all that would be on my next test. I'm going to stop sharing, but don't anybody go. I just got to see the attendance thing. One more time. Sometime next week, the end of next week, there will be a review. Don't miss the end of next week for the review. Sometime the week after next, there will be a test on chapter 4 and 5 and 6. And what did we just cover today? We covered chapter 6. I see Kevin Morales is here and Robert Morales is here. All right. Just want to make sure I got everybody. I think I'm done. Anybody who wants to stay and ask me a question can. Anybody who wants to leave can. If you want to ask me anything, you can. If you want to leave, you can. Don't miss next week. Don't worry about being late. Just don't miss the review next week. Don't worry about being late. But you're responsible for the material. But I'm not going to penalize you for being late. Just know it for the test. Yes, the genius lady. What?
I have a question on so APIPA.
Go ahead. What's the question?
So it only assigns a like a almost like a fake IP address when DHCP fails, correct?
The only time you should get that. So just for you, because you're so brilliant, the question they'll ask on the Net Plus test is, what can you conclude if you have a 168 dot something address? And you conclude three things. First, you can conclude that you were trying to use DHCP. You can also conclude that DHCP failed. And you can also conclude that APIPA gave you the address, and you can further conclude you're probably on the wrong subnet.
Got it.
You know what I mean? They always ask it backwards. Not if you had APIPA, what address would you get? They'll ask you, if you got this address, what could you conclude? And you conclude that APIPA kicked in because DHCP failed.
Got you.
You are really smart. Keep it up.
Thank you. I'm trying. Thank you so much, Professor. Have a great day.
My pleasure. You too.
Bye-bye.